to speak here and to come over and visit my pals just across the city. It's nice to see you all. So yeah, I was going to talk about, and I'm just going to try and give a sort of ideas sort of thing. I'm not going to go into a lot of technical detail, but I wanted to talk about this idea of using groupoids and sort of dynamical data to try and coordinatize C-star algebras and try and say a bit about what I mean by that and what it might be useful for. Okay, so I'll start with I start with the word C-star algebras. So I guess what's that? And the sort of half-truth that we always tell, right, when we start to talk about C-star algebras and we've got a general audience and we don't want to give the definition, is we say, oh, it's a closed star subalgebra of the bounded operators on a Hilbert space. Because we figure, oh, people know what a Hilbert space is. That's all good. And that's not untrue. It's accurate. But it's like saying a group is a collection of permutations of a set that's closed under inverses and composition. I mean, yes, that's true, but no one cares what the set is. And often the set gets in the way. The axiomatization of the group is a better description than the fact that you can realize it as permutations, right? So in the same sense, when we say that a C-star algebra is a closed star subalgebra of the bounded operators on Hilbert space, yes, it is, but not necessarily in a way that really reflects the structure that you're interested in. So I want to give you an example of why I don't love that definition. And that would be if I take the C-star algebra of the integers. Right, so what do I mean by that? I mean I'm going to take a unitary representation of the integers, right? So this is just the C-star algebra generated by, so I want some elements that look like this. They're elements un, one for each integer, and I want to know that un is un plus m, and that un star is u negative m, right? And then I take the C-star algebra generated by something like that, and the idea is that's a unitary representation of the group of integers, and that's, that's what it's supposed to be, right? Okay, so now I go back to our general theorem that's kind of like the Cayley theorem that says that every C-star algebra is bounded operators on a Hilbert space. And what Hilbert space do I get and what bounded operators do I get when I apply that construction to this C-star algebra? Well, if I do the so-called GNS construction to realize it as operators on a Hilbert space, what I realize it is as diagonal operators, not all of them, diagonal operators, on L2 of, and now it's going to be the unit circle, but with no topology. So discrete topology is regarded as a set. So I've got this massive non-separable Hilbert space. I've forgotten all about the topology on the circle, and I've just got a bunch of diagonal operators, and somehow there is some continuity of the way that they act, but I'm not seeing it because I've lost the topology in the construction. Yeah. So yes, it's an algebra of bounded operators on a Hilbert space, but that's not the Hilbert space you should put it on, right? I mean, this is not where I want to represent this. Better would be I just take operators un on L2 of z, and I do the obvious thing. So em goes to em plus n. That's the Hilbert space I want to put it on, right? That's where I get a nice copy of this C-star algebra, and it's just because because of spectral theory that I wind up with this mess instead. Yeah? Okay. So that's one example of why, even though it's an accurate description, I don't necessarily love this way of defining C-star algebras. Let me give you another example, and then I'll stop giving examples and go on to what I think might be a better way to do it. So what if I take the C-star algebra, this is a pretty famous example, generated by two elements, say S0 and S1, subject to the relations that S0, well, Si star Si is 1 is equal to S0 S0 star plus S1 S1 star. And so these relations determine what's called the Kunz algebra. It's a really famous example, right? We know all about it. That certainly comes up in, that is related to some models for quantum computation, for example, not that I claim to know a lot about that. But what happens if I do this GNS construction here? Well, again, I get some massive Hilbert space. So I wind up with operators on little L2 of, my basis is going to consist of pairs X, Y. X and Y are infinite strings in 0 and 1, and they have the same tail. Which is enormous because this is the Cantor space, right? And again, there's a lot of redundancy here. Lots of things are sort of acting the same way on big chunks of this stuff. I'm not remembering what the topology is on this set, so it's just some big uncountable set. I'm losing the topological information that C-star algebra is supposed to be good at. And better would be if I just said, well, what if I take L2 of the natural numbers? I'm sorry? Okay, so the operators are append a naught or append a 1 on the x. So S naught would put a 0 in front of the x, and S1 would put a 1 in front of the x, and then nothing else. Yeah, interesting. So they're simple looking operators, and so the point is S naught does essentially the same thing to almost everything, right? I mean, there's a lot of redundancy in that representation. And of course, there's a much nicer way to do this. This relation just says they've got orthogonal ranges as operators on Hilbert space. This relation says that they're both isometries, right? So I'd be much better off to just say, I'll send En to, so Si is going to send En to E2n plus I. Right? Just one of them takes the whole Hilbert space and puts it on the odd coordinates, and the other one puts it on the even coordinates. Much nicer, yeah? So my point is, yes, it's true that C-star algebras always have representations on Hilbert spaces, but that's not actually a very satisfactory description of them. And so what I want to do is convince you that if I use groupoids instead and look a bit closer at what's inside my C-star algebra, maybe I can get a nicer coordinatization of it, okay? All right, so sorry, try and make sure I'm actually saying what I plan to say.
Yep.
Okay. So, how do we describe C-star algebras? Well, like with groups, we axiomatize. So instead, we give an abstract definition. So a C-star algebra is a Banach star algebra, a complex, I guess, Banach star algebra, with the property that the norm of A star A is always the same as the norm of A squared. And if you want to see where that comes from, I always say, well, imagine that A was a complex number and star was complex conjugate. Right? Z bar Z is mod Z squared. Yeah. Okay. All right, so that's a much nicer definition in the sense that it just characterizes intrinsically what a C-star algebra is, but now we've got to work from that definition to some way of describing them that we can make sense of, and hopefully that encodes nice dynamics and so forth. And we then prove, so this is what this GNS construction is that I've been talking about. Well, we don't prove, Gelfand, Naimark, Segal prove that there's always a faithful representation of this as bounded operators on a Hilbert space. And you literally do the same thing that you do for groups, right? The Hilbert space is built from the C-star algebra. You take the C-star algebra, you use states to make it into a whole bunch of Hilbert spaces that it acts on by multiplication, and then you add them up. Right? So that's why these Hilbert spaces wind up being so big and complicated, because you're just writing down every possible way it can act on itself by multiplication, then completing in various norms. Yeah? Okay. But the nice thing is that when we represent on Hilbert space, so when we represent on Hilbert space, algebra talks to geometry. All right? So for example, being the orthogonal projection onto a closed subspace, just comes down to asking that P star P is equal to P. It's just an algebraic relation that characterizes the geometry, yeah? Being a unitary automorphism of the Hilbert space just boils down to U star U equals U star equals 1. Being an isometry onto a closed subspace just boils down to asking that S star S is equal to 1. You don't say anything about SS star. I guess being a partial isometry between closed subspaces, that just boils down to, well, I can write it a bunch of ways, but the quickest one is S star S, S star, no, S, S star S is equal to S. It's just an algebraic relation. So the point is, when we represent on Hilbert space, no matter how we represent on Hilbert space, the algebra tells us something about the geometry. So the algebra is intrinsic, right? So what I want to do is focus on how to realize what the C-star algebra is, what it's doing, using algebraic information, right? So that it's intrinsic to the C-star algebra. Yes?
What do you mean by partial isometry?
Oh, so partial isometry, what I mean is it annihilates some, it has a kernel, so it annihilates some closed subspace, and then on the orthogonal complement of that subspace, it's an isometry onto some other closed subspace. Yeah, thank you. Yeah. It's the C-star algebraic equivalent of a partially defined map between sets or something, right? It has a domain that's not the whole thing and it sends it bijectively to some range. That's the way to think about it. Yeah. Okay. Okay, there is another trick, and this is where I get to actually use a nice abstract theorem. So, you know, I said the Gelfand-Naimark-Segul theorem is an accurate description, but it's perhaps not very satisfactory. But for commutative C-star algebras, there is a theorem due to Gelfand-Naimark that is satisfactory. Right? It's a really nice abstract theorem, and it says, so theorem, (1943), if you've got a commutative C-star algebra, then the map, which sends A to A hat, and I'll say what I mean in a second, is an isomorphism from A to the continuous functions on A hat, capital A hat, and by capital A hat I mean homomorphisms, so star homomorphisms from A to the complex numbers, non-zero, I guess. Right? So A hat here is just the usual dual, right? Like, you know, from ordinary duality. So A hat of phi really means phi of A. It's just the evaluation functional, yeah? Okay. Okay, this is nice because A hat, this thing is intrinsic, and it really does reflect the properties of the algebraic properties of the C-star algebra that you've got in hand, right? Because it's measuring the algebraic properties. It's got an intrinsic topology, just the weak star topology, and you know stuff about it. So this is a useful description. And for example, let's go back to our C-star of Z example. So what would a homomorphism, remind you what C-star of Z was? I had these elements UN, right? When I multiply them, I add. When I take the adjoint, when I take the star, I get the negative, right? So a homomorphism from that to the complex numbers is going to be determined by what I do to U sub 1. Yeah? If I want it to be bounded, then all the powers of the image of U sub 1 need to, like, they have to be bounded, uniformly boundable. The only way that happens is if it's on the unit circle, right? So I have to assign an element of the unit circle to 1. And after I do that, everything's determined. And any element of the unit circle will do. So this is just, oops, I'm sorry. This is just the continuous functions on the circle because A hat is the circle, yeah? And this, so it's really just Pontryagin duality, but realised through C-star algebras. Is what, sorry? Why do we know it's metrizable? I mean, it's always metrizable. So in general, this is always, in this instance, a locally compact Hausdorff space. And as long as A is, even if A is not separable, it's metrizable, but I'm going to just focus on A being separable to make things easy, and then it's a separable. It's locally compact. It's compact if A is unital, precisely when A is unital. So, sorry, it should have been C0 of A hat, I'm sorry. So if A is unital, it's C of A hat, otherwise it's C0 of A hat. Thanks. Yeah. Okay, any questions? All right, I want to exploit that theorem, but I want to use it to describe more general C-star algebras dynamically as much as I can, right? So I want a picture for general C-star algebras that makes use of that Gelfand duality. Okay, well, the starting point is that there's a neat consequence of this theorem for just arbitrary elements of the C-star algebra. Let me just move that down so we can see more stuff. Okay, so there's a neat consequence that tells us something about arbitrary elements of a C-star algebra. So, consequence. So let's say I've got a C-star algebra that I've picked up on the street and I'm trying to figure out what it is. Yeah? And I pick an element out of it. So I pick A in A. Well, I can always do this. Once I've got an element of a C-star algebra, I can always multiply it by its adjoint. Right, now, you've got to think of it. I mean, this is an involution, right? So it reverses the order of multiplication and it undoes itself. So if I take the adjoint of A star A, I just get A star A back, right? This is self-adjoint. And it obviously commutes with itself because everything commutes with itself. Yeah. So if I took the span of powers of A star A and closed it up, I would get a C-star subalgebra that was commutative. So it'd be the continuous functions on something. Yeah. So we call this C star of A, star A, sorry. And that's going to be isomorphic to C0 of something which I will call delta A star A. Actually, I'll call it sigma of A star A. I could tell you more about what this, I mean, it is the spectrum, for if you care. It's the complex numbers lambda such that A star A minus lambda is not invertible in the minimal unitization, but I don't care. It's the continuous functions on something, all right? And I'm actually going to want to think of it as just continuous functions on something abstract, because in a second I'm going to want to stitch a bunch of these together into something more global that isn't quite like that. So the spectrum is compact when you include 0, but including 0 amounts to including 1 as an additional element. So then in order to get the spectrum to be compact, you want to take the C-star subalgebra generated by A star A and an adjoined unit. Otherwise, you don't get 0 in the spectrum and you get a locally compact set. Yep. Thanks. Okay. Now, I'm now going to, so I said something about representation theory in the title, right? And I've had at least one person tell me I need to be held to my promises. So, okay, so representation theory. So in representation theory, when I want to know that the representations of two rings or algebras or whatever are the same, I look for a Morita equivalence between them, right? So I look for a Morita context. So in representation theory, a Morita context between rings, say, A and B is modules. So I've gotten A, B module R and a B, A module S. And I want to know that when I take the balanced tensor products, I get back the two rings as the trivial modules over themselves, right? And when I've got such a pair of things, I can induce representations of A to representations of B by tensoring with S, and I can induce representations of B to representations of A by tensoring with R And so I get a correspondence between the representation theories, right? Well, exactly the same thing works for C-star algebras, but it's even nicer because we've got this involution floating around. So in C-star algebras, we have the same idea, and this is really due to Riefel, but we only need one module, so X is going to be an A, B module, but it's going to have inner products on both sides. So it's going to have sort of an A-valued inner product and a B-valued inner product that interact nicely with each other. So with inner products, and these play the role of allowing you to pair an element of X with an element of its sort of conjugate module to get out elements of A and B. So the idea is that then, so X star, the conjugate module, is playing the role of the other half of Morita context. Again, it doesn't really matter what the details are, but the point is that when I've got a setup like this, it induces, so this induces a homeomorphism from irreducible representations of the two C-star algebras. Right? So I can do Morita theory in C-star algebras as long as I've got one of these sort of modules with two inner products. All right, I've gone a bit technical, but there's an example of such a module staring us in the face, and it's not particularly complicated to write down. And that is, say I take my element A that I started with in my C-star algebra, right? So the example, I take my element A, I multiply it on the right by the C-star algebra generated by A star A, or, same thing, on the left by the C-star algebra generated by AA star, and it's not too hard to convince yourself that they're the same thing, right? Because A times A star A and A star A times A are the same thing, yeah? So it's not too hard to convince yourself that they're the same. That's an example of one of these Morita equivalences between this commutative C-star algebra and this commutative C-star algebra. What are the inner products? Well, if I wanted to do xy on this side, I just do xy star. And if I wanted to do xy on this side, I'd do x star y. It's just right there in the algebra, yeah? All right, so every element of my C-star algebra determines a homeomorphism between irreducible representations of A star A and irreducible representation C-star algebra of A star A and of AA star. But these are just the algebras of functions on a space. What are the irreducible representations of those? They're all one-dimensional, yeah? They're just the evaluation maps. So what I get is a homeomorphism alpha sub A from the spectrum of A star A to the spectrum of AA star. Again, I don't really care what these are, I just care that they're the things that they were for algebras of functions on. Okay?
Sorry, just a question. The inner products are meant to take value in A for one of them and the other one's meant to be B?
That's right, yep. Yeah, sorry, did I write that down? Yeah, so this one takes values in A, this one takes values in B. And the subscript is supposed to tell you which algebra it's in. Yep, yeah, sorry, thank you. Good. Okay, so what's that saying? That's now saying that locally a C-star algebra is some dynamics between some topological spaces. Yeah, when I pick an element of a C-star algebra, it gives me a little patch of dynamics, a little locally defined homeomorphism between two things. All good?
And all representations here are meant to be on Hilbert spaces? Or...
Yeah, that's right. They're going to be on Hilbert spaces. So yes, I'm always going to, when I represent a C-star algebra, I always mean bi-bounded operators on a Hilbert space. Yep, exactly. Yeah. So what I'm trying to do effectively is to localize and get better control over that GNS sort of thing, right? To get nice representations. Okay. So I want to now go back to the big picture. And I want to tell you what I want to try and do with this. So when I say a closed star subalgebra of B of H, what I want to picture is something that looks like this. So I really want to believe that that means that A looks like a set of things that look like this. A great big bloody matrix. I've got diagonal entries down here. I want to put sort of an AXX, you know, down the diagonal. So there's some diagonal entries, and then I've got some AXYs elsewhere, and they're mapping between different vectors in the Hilbert space, right? So just B of H is a bunch of matrices, but they're infinite matrices, and I can't really say exactly which matrices are bounded operators, right? But they're big infinite matrices, yeah? So that's what I want to think. But of course, what we discovered was that that's not really what it looks like when we apply the theorem, because, for example, when I take C star of Z, there are lots of constraints on what these diagonal entries look like, and they're not immediately apparent to us when I write down the basis, right? Because the basis doesn't know anything about topology. So this is what I'd like a coordinatization of a C star algebra to look like, but it doesn't really if I just use the Gelfand-Naimark-Segall theorem, like the abstract theorem. So what I want to do instead is to replace it. So this doesn't work. So I guess this is not quite right. And the point is, yes, the elements of A can be realized as infinite matrices, but it's almost impossible to say which ones. I know I can't, it's very hard to say which matrices belong to A. So what I want instead is to do something like this. So I want it to be a set of things that look like this. Now I'm going to put down here some topological space. Right? Inside this topological space, when I take an element of my C star algebra, I might get a little bit that looks like the spectrum of A star A. And somewhere else, I get a little bit that looks like the spectrum of A star. And I know that this Morita equivalence that I built gives me a map between them, a homeomorphism between them, right? So I've got a little bit of dynamics from some bit of some, I mean, I've got to put this stuff together, I've got to manufacture it from somewhere. A little bit of dynamics that goes from one bit of this to another one, yeah? That's from the homeomorphism alpha A. And I'm sure you'll believe me if I say that XA star, the Hilbert thingamy-bob that I get from the Morita context that I get from the adjoint of A, is the same thing as the conjugate module of XA. I mean, you could believe that if I just take the adjoint of everything in this thing, I'd get something in the corresponding thing for A star, right? I hope you'll believe that. Which means that this arrow can be reversed using alpha A star, right? Because X tends to X star and X star tends to X are supposed to be the two C star algebras at either end in a canonical way. Yeah? So I've actually got not just a little bit of dynamics, but a little bit of reversible dynamics, and the reversibility is encoded in the C star algebra as well. Yeah? I know I've got the bits of dynamics, all I need to do is patch them together. Right? And then I should get some nice global description of my C star algebra. Yeah? Okay, so that's the objective. And that's where groupoids come in. So what's a groupoid? So a groupoid is a small category with inverses But I like to think of it as basically like a group, but multiplication partially defined. Yeah, so I can't multiply arbitrary pairs. I'm only allowed to multiply things some of the time. When am I allowed to multiply things? Well, the idea is that I've got so there is and for today, I'm just going to, when I say groupoid, I always mean locally compact Hausdorff groupoid because I'm allowing myself to be a bit fast and loose. So there is a locally compact Hausdorff space X sitting inside G, so let's call the groupoid G, sitting inside G. And then for alpha in G, alpha, alpha inverse, and alpha inverse alpha belong to that subspace. This is like a set of units or a topological space of units. I'm only allowed to multiply things if, so I'm going to call this the range of alpha. I'm going to call this the source of alpha, because if you imagine alpha being an arrow, going backwards along alpha and then forwards along alpha, I'd wind up at its range. Going the other way around, I'd wind up as its source, right? And I'm only allowed to compose things if the range and the source match up like they do in a category, and then the idea is that range of alpha times alpha is equal to alpha is equal to alpha times the source of alpha, right? So they act as identities where they can. Yeah, that's what a groupoid is. And it's a locally compact Hausdorff. The whole thing is going to be locally compact Hausdorff. All of the operations are going to be continuous, et cetera, et cetera. So it's nice. But that's what a groupoid is. And the point is I've got the building blocks of a groupoid right here. I've got a topological space, and I've got a bunch of arrows that are reversible. All I've got to do is stitch them together. Yeah? Does that make sense?
Sorry, so X is meant to be like a subcategory as well?
Yeah, but it's just the units. It's the subcategory consisting only of the units of G. Like it's literally the set of units of G. Yep. Okay? Okay, so how and when can I stitch these things together to get one of those things is the question. So, sorry, how am I going for time? Yeah. Good. Okay, so let's say that A is a C-star algebra. Well then C is going to be a Cartan subalgebra if it is maximal abelian there exists a norm-decreasing idempotent, idempotent and I should insist that if phi of A star A is 0, then A is 0. So it's sort of faithful somehow. It keeps track of the non-zero elements. Think if I had a great big space like G and a Clopen subspace X, think about restricting functions. So I've got a function on G, I restrict it to a function on X. That's the sort of thing. Okay? Or think about the map that takes a matrix and picks out its diagonal. That's a really good example. And then the third thing is A should be the closed span of n of A, n of C, normalizers of C, and by that I just mean elements n such that n star C n and n C n star are contained in C. And if you want some motivation for that, think about how matrix units behave when you conjugate diagonal matrices by them, right? Matrix units take diagonal matrices back into diagonal matrices when you conjugate. So they're sort of like, these are things like, they're the analogues of something sitting in a little matrix unit patch somewhere. Okay. Oops. Well, every one of those normalizers gives me a little locally defined, one of these little Merida contexts, these X things. Yeah. So for n in, or m and n, so if I take two of these normalizers that I've just said span the C-star algebra and I look at the balanced tensor product of the Merida modules that come from them between their little locally defined topological spaces, this is going to be canonically the same as xmn. So multiplication in the C-star algebra sort of indicates what happens when I glue the dynamics together, because this represents alpha m composed with alpha n, and this represents alpha mn, just by construction, right? These little homeomorphisms glue together. If n is a normalizer, then so is its adjoint, because the definition is completely symmetric. So this is alpha n inverse, and this is alpha n star. So that represents reversing things with my blue arrows over on the other board. Yeah. And these act, the isomorphism classes. So this is isomorphism class. Is an inverse semigroup. If you don't know what an inverse semigroup is, just think a semigroup except that things have a locally defined sort of, they're trying as hard as they can to be inverses in a semigroup. Yeah? Okay. And it acts on the spectrum of C, because every one of these little C star of n star n sits inside C. The reason for that is that these three conditions guarantee that C contains an approximate unit for the C star algebra. So I can put an approximate unit in between the n and the n star, and I keep landing in C, and then I take the limit. Right? So automatically, n star and n star are in my C. So the C star algebras they generate are C star subalgebras of C, and so they correspond to little subsets of the spectrum of C. Okay? So I can form the groupoid of germs of this action. Right? So I take pairs m, comma, x. X belongs to C hat. So this is mx. M is a normalizer. X is in C hat. And I really want to think of x as being in the spectrum of m star m, sitting inside C hat. And then I quotient by mx is the same as n y if x equals y, and alpha m agrees with alpha n near x, like on a neighbourhood of x. Yeah, so the germ of the action. So I can build this groupoid of germs. It's one of these doovers that I talked about on the previous board. Moreover, I'm conscious that I'm a bit short of time, so I'll just say this and then stop. So moreover, each xn, so each one of these Hilbert modules, it's a Hilbert module between these commutative C-star algebras, right? It is automatically, because of the fact that it's an imprimative module, a Merida equivalence module, it is automatically the sections of a line bundle, a bundle of complex lines parameterized by the spectrum of n star n. So is a line bundle. And if you want to see it, I can sort of tell you what the fibers are. I take my xn, that was n times the C-star algebra generated by n star n, right? And then I quotient by, so I take xn and I multiply by the functions C0 of, spectrum of n star n, take out some point. Right, so if I take the algebra of functions supported on the spectrum of n star n, and then I take out 1 point, set it 0 there, and take the quotient, I get a one-dimensional thing, and hopefully you're willing to believe that that makes this a one-dimensional thing, and I get a complex line. Right, and the upshot is that I get what's called a Fell bundle B, which is the union of the, let's call this x n little x, point whatever. So the union of these guys has a natural topology that it gets from, I mean, I fix an n and I let the point vary. That gives me a continuous section. So it defines a topology. If I take two different normalizers, I take m star n and I apply my map phi to it, and I get a function defined on the unit space that is not zero, so I can take its phase. That gives me a unitary valued, one-dimensional unitary valued function that I can use to glue patches of my line bundle together. So I glue over those maps and I wind up with this Feld bundle. And it's a Feld bundle sitting over G in the sense that for every element of this bundle, I mean, it's a line, but it corresponds to a unique point in G below it. And then the theorem, I guess, that I will finish with. And this is really, I'll say Feldman-Moore, but also, well, so Feldman-Moore did this for von Neumann algebras, where you don't have to worry about the topology because everything's measurable. But then I'll say Renault, but also I'll put Kumjian's name. Because he worked out a special case, but a very important special case first. And the theorem basically says that Cartan pairs correspond exactly to Feld line bundles. Right? So I can go back and forth between these two pictures. If I've got one of these Feld line bundles, the algebra of compactly supported sections from the groupoid back into the bundle is a star algebra, and I can complete it in a canonical way, and I get a C-star algebra. And if I started with a Cartan pair, built one of these things, and then went back via the construction, I'd get back to where I started, canonically, and vice versa. Right? So I started off with a C-star algebra with a little bit of extra data, this abelian subalgebra, and I've got a really nice geometric realization of it in terms of some dynamics on a topological space, roughly speaking. I was going to maybe say a little bit about why that's useful, but I will stop there because I've used my time up. So thank you very much.
So I'm aware of Feldman-Moore, which is actually saying that the measurable equivalence relation is arbitrary for some group action. And in this this is a little bit different language.
That's right.
So what do you mean when that is?
So the point is, so Feldman and Moore, that's exactly right. And the point is that in Feldman and Moore, how do you get the group action? So the group is you take all of the local measure preserving maps that you get from little bits of something, and then you just glue them together into global ones, right? So you just cut them up, disjointify them, and glue them together into global ones, which you can do because everything's Borel. So you can cut things up however you want. In the context of C-star algebras, you've got topology to worry about, so you can't cut things up into disjoint sets anymore. So all you can do is define it locally and then say how you transition on overlaps between the domains of these things. So instead of getting a group action, you get some sort of pseudo group action like local, and that's what the inverse semi. So the inverse semi group here is trying to be the group from Feldman and Moore. Yeah. And I guess I should say then the Feld line bundle is keeping track of what the co-cycle keeps track of in Feldman Moore, right? Because again, if I've got a Borel bundle, I can always choose a Borel section for it, so I can turn the bundle into a co-cycle. But I can't do that necessarily topologically. It might not be globally trivial. So, yeah. Yes?
I didn't quite get what it means to be like a bundle over a groupoid.
Yeah, okay, so all I mean is, so think of it as this is just a topological space and this is a line bundle over that topological space, a principal line bundle. But then I'm going to insist that there's a way to multiply elements in here that's compatible with multiplying elements in here.
So the topology on the groupoid G really is just on the objects.
Yeah, so, well, no, so the idea is I can lift the topology on the objects to a topology on the whole groupoid because the groupoid is basically, it consists of the topological, it's the union of the bundles of arrows that correspond to these normalizers, right? So every time I've got an arrow, it sits inside one of these normalizers and there's a bundle of arrows nearby. That's a homeomorphism between two bits of the unit space. So I just give it the topology that lifts up from that patch of the unit space. And then I make those, then I stitch all those together and I get a topology.
Is it true that if you have a ring, then you will find actually the C star it's a ring, as you did with Z? Then you can ask what is the nice representation of that in terms of the
So good question. There are some instances of the C-star algebras generated by rings. Probably Nathan knows more about the answer to that question of when you can and can't associate a C-star algebra to a ring than I do.
Yeah, Shinley is
Yeah.
the ring C-star stuff.
Yeah.
I don't know exactly what assumption it is.
Yeah.
There is a ring.
So yeah, like I think there are some issues because, like if you take a group, there's always a group C-star algebra. Like, because if you take a unitary representation, you always wind up with something bounded. But for example, if you take a Hecker pair and you look at the associated Hecker algebra, you can construct examples where there is no bound on the norms of star representations when you try and write them down, right? So you have to be careful because you can't always build a universal C-star algebra.
So what were you going to say this was useful for if you have time?
Right. So I guess all I was going to say was, the point is, once you've got some dynamics, for example, I can characterize whether a C-star algebra of one of these Fell line bundles is simple, or what its ideal structure is, or what the traces are on it, or whether it's nuclear, which is or satisfies the so-called universal coefficients theorem between KK theory and K theory, all sorts of stuff in terms of the dynamics of the groupoid in a way that's checkable, right? So whereas all of those questions, if you just handed an abstract C-star algebra, are really hard. So if I can find a Cartan subalgebra inside a C-star algebra, then in particular, I can then start to answer those questions about that C-star algebra in terms of that decomposition. I guess the other thing is, so there's two other parts to the answer. So one is that there's this general principle that I think Barbarian espoused, which is that whenever you're doing something with C-star algebras, if you're doing it right, there should be some solid algebra sitting underneath it that explains what's going on. Like, you've got to do the analysis, but there should be some solid algebra sitting underneath it. And this picture does extend really nicely to abstract algebras. And what I've found really nice about it is that you would never think to, in the first instance, you wouldn't think to look for this sort of thing in abstract algebra. It's just, you don't sort of, you look for this sort of structure in a C-star algebra because you're used to the Gelfand duality. But then it turns out you can sort of characterize abstract algebras with a subalgebra that behave like dynamics using the same ideas, just by sort of thinking, well, how do I abstract away the analysis? And I kind of like that you can then get some flow of information back and forth between the two fields that you wouldn't see otherwise. So yeah.
Okay, so when you get a Cartan?
That's a really good question. So that's the next big question, right? So I guess now we're at the point where, so we're lagging von Neumann algebra theory by about 30 years, right? So we're now at the point where, okay, if we've got a Cartan subalgebra, we can say all sorts of nice things. So the next question is, when is there one? When there is one, how many are there? Can we classify them up to, conjugacy by automorphism? What's the structure of all of the Cartans inside something? And it looks like it's a very hard problem. So for example, if I take the infinite tensor product of copies of the 2x2 matrices, I get the UHF algebra of type 2 infinity. So it kind of looks like it's an AF algebra, and it's trying to look like the hyperfinite 2-1 factor, right? It's trying to look like R. In that C-star algebra, there are uncountably many non-conjugate Cartan subalgebras that all look like the algebra of functions on the Cantor set. And there are also Cartans that look like the algebra of functions on the circle, even though the thing looks like it should be totally disconnected. So it's complicated. That's a really hard question. But an excellent question.
Well, if there are no questions, we can thank Aidan again.